Let's look at an example where we analyze this polynomial function, x squared times x minus 2 cubed times x plus 1. If you'll notice, the polynomial is given to you already in factored form, which will make it a little bit easier. Let's first talk about end behavior. We want to find our leading coefficient and our highest degree. If you notice, we have a 1 in front of this and a 1 here and a 1 here. So we know our leading coefficient is going to be 1. Now let's figure out the degree of this polynomial. Right here we have x squared. Here we will end up with an x cubed. And here we will end up with an x. And if we multiply all those together, we end up adding our exponents. 2 plus 3 is 5. Plus 1 more is 6. So the degree of this guy is going to be 6. Now within behavior, when we get all the way far left and all the way far right, our graph begins to behave like our leading term. That's what this is asking right here. The graph of f behaves like y equals, and this is where they want the leading term. So we're going to say 1x to the 6th. If we were to multiply all this out, that would be our leading term. Next, let's find the x and y intercepts of the graph of this function. So to find the x-intercepts, that is where our graph crosses the x-axis. And at the x-axis, y equals 0. So we are going to set all of this equal to 0 and solve. And these are all factors. And when you set factors equal to 0, we have to set each factor equal to 0. So to find our x-intercepts, we are going to set each factor equal to 0 and solve. So x squared equals 0, and x minus 2 equals 0, and x plus 1 equals 0. So here we end up with a x-intercept at x equals 0. Here we have an x-intercept at x equals positive 2, and here we have an x-intercept at x equals negative 1. For y-intercepts, we are going to plug in 0 for x and solve for y. If we plug in 0 for x to our original function right here, everywhere we see an x, we're going to replace it with a 0. So we're going to say that our y-intercepts equal 0 squared times negative 2 cubed, 0 minus 2 is negative 2, times 1. And when we multiply all that together, we find that the y-intercept is 0. Okay, now we're going to talk about the zeros and their multiplicity. We've really done all the hard work to find the zeros. The zeros are where your equation is set equal to 0. And so it's the same process as finding the x-intercepts. X-intercepts are only your real zeros. Here, all of these are real, so they are going to be our zeros as well. So we can say that x equals 0 has a multiplicity of, now if we look up here, this is where x equals 0 came from, so it has a multiplicity of 2, which is even. And an even multiplicity touches the x-axis and turns back around. All right, let's look at the next one. X equals 2 came from this factor right here. It's going to have a multiplicity of 3, and that is odd. An odd multiplicity crosses the x-axis. A multiplicity of 3, if you remember, crosses like a cubic. And our last 0 is going to be x equals negative 1, and it has a multiplicity of 1, and so it's odd, and it crosses. And so we can write multiplicity of 1. I left that out. All right. With all of that information, we can do a pretty good job sketching this graph with no calculator. So let's try that. So I'm going to just draw myself an x-axis here. And we have 0, 2, and 1. So I'm going to give myself a y-axis as well. First thing I'm going to do is I'm just going to put a point at every 0. So we know we're going to cross here at 0, 0. And we also know we're going to cross at -1. So we can call that -1. And we know we're going to cross at +2. So there's the places that we're going to cross our graph. Now we're not going to be able to do a perfect graph, but using our end behavior as well as multiplicity, we can get a good idea. The right side behavior is determined by our leading coefficient, whether it's positive or negative. And if you notice right here, our leading coefficient is 1, and so we know it's positive. Positive means that we rise on the very right side. So I'm just going to kind of give myself a little rise over here. With a degree of 6, we know that the far left side is going to do the same thing because the degree is even, means my end behavior is the same. So I'm going to come over here and give it a little up arrow as well. Now let's go to each individual 0. I'm going to start on the left with x equals -1. That has a multiplicity of 1. So we know it's going to cross like a line. Next, we have x squared, which has a multiplicity of 2, which means right here we are going to have parabolic behavior. It's going to look a little bit like a parabola. And so I'm just going to give that a little turn to make it go around. And then our very last one over here at +2 has odd multiplicity. And that means it crosses, but you'll notice that it's a 3. So it means it crosses like a cubic, and it's going to be a little bit hard to tell because my graph is so small. But basically, I want to kind of make it look like, oh, I didn't do a very good job like that. It's not going to cross like a line there. So it's going to do something to that effect. Most important is that this looks like a cubic. And what does a cubic look like? Like that. And so this would be your +2. Okay, so there's our bad sketch, but at least we have a good idea. So I'm going to get my calculator out now, and we are going to plug it in to y equals. So let's get this plugged in. And you'll notice I have it already in y equals, and let's look at our graph. Well, my graph doesn't look quite the same, but it is kind of similar. You can see that I have this kind of parabola right here as well on the graph. And then here is that cubic behavior at x equals 2. And here at x equals -1, it crosses very linear, like a line. On number 5, it says approximate the turning points. A turning point is where you go from increasing to decreasing. An inflection point is where it kind of flattens out, but it remains either increasing or decreasing. It does not change over. So be careful. This particular graph has a turning point here, and a turning point here, and a turning point here. This is called an inflection point or a saddle point. It does not change over. So we only have 3 turning points that we are going to approximate. We already know this one. It crosses at 0, 0. So that is that turning point. Let's figure out this one and this one using our calculator. We're going to use the calc button, and we're going to go to second calc. And both of those, if you see right here, we're going to do this one first. That is a minimum. So we're going to use number 3, minimum, and we're going to follow the directions. It says left bound. This is the approximate point. So we're going to move our cursor a little to the left, and hit enter. Now you'll notice it says right bound. We'll move to the right, hit enter again. And so we know that this turning point right here is negative 0.74 comma negative 0.9, oh wait, excuse me, negative 2.93. Negative 2.93. Now let's find this turning point. This turning point right here, or this guy, is also a minimum. So let's do it again. Second trace, number 3. But we're going to move our cursor over here. And you need to make sure that you put your cursor to the left of the minimum. So just make sure it's all the way to the left, hit enter, and then move it to where you know it's to the right and hit enter one more time. And so this turning point right here, and I'm going to draw a line right here. This turning point right here is 0.90 comma negative 2.05. So there is that turning point. Okay, now we're ready to find domain and range and where our graph is increasing and decreasing. Domain of all polynomial functions is all real numbers. Range is how far up and down your graph goes. So the range of this polynomial is going to be from here all the way up, you'll see. So what is the y value of that point? It is negative 2.93 approximately. Okay, so domain, we decided, is at negative infinity to positive infinity. Range, we're going to start at the lowest value and it touches that value. And so we're going to make sure we use brackets and use negative 2.93. And we're going to go all the way to positive infinity because it looks like it goes forever up from there. Our last piece is finding where this graph is increasing and decreasing. Remember, with increasing and decreasing, we use interval notation, and we always read the graph from left to right. I imagine it like a ride. We want to ride on top of this graph like this. And so we're going to be decreasing until this point, and then we will increase from here to here, and then we will decrease to this point, and then we will increase from here to here. So it's important that we use those turning points. On which interval is the function increasing is the first question. So where is it increasing? From this minimum value all the way to the origin. So we only use the x values to describe. So we're going to start off with negative 7.4. Oh, excuse me, I put my decimal in the wrong spot. Let's clean that up. Negative 0.74, and we're going to go increasing all the way to when x equals 0. Then, are we increasing anywhere else? Yes, we are. From this turning point all the way to infinity. Now, this was this weird kind of inflection point where it looks like this. But if you'll notice, we are increasing this whole way. So we don't need to have a break in that interval. So from 0.90 all the way to infinity. So 0.90 to infinity. Now let's talk decreasing. Decreasing from the very far left right here, negative infinity all the way to this x value. So negative infinity to negative 0.74. And then we start at the origin and we decrease all the way to this value right here, which is 0.90. So from 0 to 0.90. And so those are the two intervals where we are increasing and decreasing.